Last time we have studied the different system calls such as open, read, write, close, lseek, change root, change directory. Now we are going to study the next system calls change ownership and a change mode. So change ownership or change mode, that is access permission for reading, writing and executing of a file, are operations on the inode, not the file. So syntax of a change ownership of system call is chown. Then arguments are path name, ownership and group, owner and group. So path name is a name of file, owner. To change owner of the file, kernel converts a file name to inode using algorithm name I. The process owner must be a super user or match that of file owner. Kernel then assigns new owner and group to the file, clears a set user and set group flags that releases via inode via algorithm I put. So whenever user want to change owner of this file, so first change with name of that file with the name of I, name I algorithm, and the process owner must be a super user or match of that file owner. The process cannot give away something that do not be doing it, belong to it. The kernel then assigns new owner and group to the file, clears at the set user, set group flags and releases inode via algorithm with the help of the algorithm I put. After the change of ownership, the old owner loses the ownership access rights to that file. This is the description of chown system call changing ownership. Next system call is change mode, that is ch mode. Syntax of this is ch mode with arguments as a path name and mode. It is a similar, it have similar process to change mode as that of change owner. So changing mode of flags in the inode instead of change of ownership. So your path name will be changed with the help of name I algorithm by kernel, which converts the file name to an inode, and mode will be changed with the flags, that is instead of read, write, execute. Suppose a file contains a read and a write permissions. We don't want a write permission. Instead of write, we want execute. Then we can change instead of write to execute. Then next a system call is a stat and fstat. The system calls a stat and fstat allow processes to query, that is a status of file. Stat for a status of that file, returning information such as file type, file ownership, access permission, file size, number of links, inode number, and file access time. So stat indicates that status of that file, that is a general information regarding that file, that is file type, ownership, then different access permission, then what is the size of that file, then number of links, number of inodes, inode number, and how many number of times a file is accessed. So syntax of this system call is a stat with parameter, a path name, and stat buffer. So path name is name of file. So file descriptor FD, which is returned by the previous open call. Then stat buffer is address of data structure in the user process that will contain a status information of file on the completion of the call. Then fstat, the system call syntax is fstat fd fstat. So that is a file descriptor which is shown by the previously open call. And stat buffer is address of data structure in the user process that will contain status information of the file. The system call simply write fields of inode into that stat buffer. Then next system call is pipes. So pipes allow data transfer in first out manner, that is in the sequence of queue, execution of queue in data structure is first in first out or last in last out. Same execution of the system call is first in first out manner, and they allow synchronization of process execution. Their implementation allows processes to communicate even though they don't know what processes are on the other end of the pipe. Whenever the process is going to start execution from one end, then what is at the other end, what happens, that process don't know. The traditional implementation of pipes uses file system for a data storage. There are two types of pipes: named pipes and unnamed pipes. There are two types of pipes: named pipes and unnamed pipes. So unnamed pipes identical with named pipes, except for the way that the processes initially access them. Processes use open system call for named pipes. Processes use open system call for named pipes, but pipe system call to create unnamed pipe. Afterwards, processes use a regular system call for files such as read, write, close when manipulating pipes. Only related processes, descendants of a process that issued the pipe calls, can share access to unnamed pipe. See, in this figure, there are process A, process B, process C, process D, and process E. There are total 5 processes. In this figure, the process B creates a pipe, then spans with process D and process E. Process B creates a pipe. Process B creates a pipe, and then process B is divided into two parts, process D and process E. The three processes share the pipe. process B, process D, and process E. But process A and C cannot share these pipe because process A is a root of, or it is a parent process of process B. Process B calls the pipe its own purpose for execution of process B, and process D and process E are children of process B. That's why process B, D, E share the pipe, but process A and process C cannot share the pipe. However, all processes can access named pipe regardless of their relationship, subject to usual file permission. With the help of usual file permission, all processes access named pipe because unnamed pipes are more common. They will be present first. With the help of access permission, all processes access the named pipes. But whenever particular pipe is called by a particular process, then other processes cannot access that pipe, cannot share that pipe. It will be shared with its children processes. Then syntax of pipe system call, that is a pipe, and then argument is a file descriptor pointer, FDPTR. So file descriptor pointer is a pointer integer array that will contain the two file descriptors for reading and writing the pipe. Because kernel implements pipe in the file system and pipe does not exist before its use. So kernel must assign inode for that pipe which is created. So here point file descriptor table, file descriptor pointer, which is a pointer, that is integer array which contains two file descriptors for reading and writing that pipe. Whenever kernel implements pipe in the file system, the pipe does not exist before its use. So that kernel must assign an inode for that pipe. So it also allocates a pair of user file descriptors and corresponding the file table entries for pipe. That is one file descriptor for reading from the pipe and other file descriptor for writing to the pipe. So whenever output of one pipe, where the output of one pipe is the input of other pipe. So there are two pointers are used. One pointer for reading the contents, that is the output of first file or first pipe, and a second pointer is used, that is writing the contents to the second pipe, which is the input for a second pipe. So this is the algorithm for the creation of unnamed pipe. See this algorithm: pipe, input none, output read a file descriptor, then write file descriptor. So whenever assign a new inode from the pipe device with the help of inode allocation algorithm. Allocate the file table entry for reading, another for writing. Initialize file table entries to point to new inode. Allocate user file descriptor for reading, another for writing. Initialize to point to respective file table entries. Set inode reference count to 2, initialize count inode readers and writers to 1. See this algorithm carefully for creation of unnamed pipes. For creation of unknown pipes, kernel assigns an inode for a pipe from the file system designated the pipe device using algorithm alloc. So with the help of ialloc algorithm, assign new inode for pipe device from pipe device. A pipe device is just a file system from which kernel can assign inodes and data blocks for the pipes. System administrators specify a pipe device during system configuration, and it may be identical to another file system. While a pipe is active, kernel cannot reassign the pipe inode and data blocks to another file. That is, whenever a pipe is assigned to a particular file and file execution, that is, pipe is active for that execution of file. During this time, kernel cannot reassign the same pipe with inode and data block to another file. Kernel then allocates two file table entries for read and write descriptors respectively and updates the bookkeeping information in core inode. So each table entry records how many instances of a file are open for reading and for writing. File table descriptor shows the entries for the opening of pipes for reading and writing, initially one for each file table entry, and the inode reference count indicates how many times the pipe was opened. Initially two, that is one for each table entry for reading and for writing. Finally, the inode records byte offsets in a pipe. Finally, the inode records byte offsets in the pipe where the next read or write pipe will start. Whenever the execution of first file is completed by pipe 1, then second pipe will be start from that end of first pipe. So maintaining byte offset into the inode allows convenient first in first out access to the pipe data and differs from the regular files where the offset is maintained in the file table. So execution of pipes in the form of first in first out access, which is a differ from regular files, where the offset is maintained in the file table. Processors cannot adjust them. Processors cannot adjust them via L6 system call. So random access input output to the file is not possible. L6 system call cannot adjust. With the help of L6 system call, processes cannot adjust the pipes. So there is no random access of input output devices to a pipe. Then opening a named pipe. We have seen there are two types of pipes, named pipes and unnamed pipes. So here we are going to study opening a named pipe. So a named pipe is a file whose semantics are same as that of the unnamed pipes. Semantics are same. Semantics are same of named pipe as well as unnamed pipe, but it has a directory entry and it is accessible by path name where in named pipe. Processes open named pipe in the same way that is open a regular file, and hence processes are not closely related, can communicate. Named pipes permanently exist in file system hierarchy. Named pipes permanently exist in file system hierarchy, but unnamed pipes are transient. But unnamed pipes are transient when all processes finish. When all processes finish using the pipe, the kernel reclaims its inode. Whenever the execution of all processes done by using the pipe, then kernel claims for its inode, and the algorithm for opening a named pipe is identical to the algorithm for opening a regular file. Here, algorithm, whatever algorithm we have used opening a regular file is the same algorithm for opening a named pipe. However, before completing the system call, kernel increments read or write counts in inode, indicating the number of processes that have the named pipe open for reading or writing. A process that opens a named pipe for reading will sleep until another process opens a named pipe for writing and vice versa. Whenever a process open named pipe for reading, at that time suppose another process open same pipe for writing, then a reading process will be go to the sleeping mode until writing does not complete. Whenever writing complete, then reading processes wake up for reading purpose. At that time writing processes which are writing in mode, they are go to the sleep mode and vice versa. That is only one mode will be open, which is a reading mode or a writing mode at a one time in a single pipe, which makes no sense for a pipe to be open for reading if there is no hope for receive the data. That is, whenever reading is start, there is no writing, so there is no hope or not receiving that read data to the pipe. Same case for writing also. So depending on whether the process opens, depending on whether the process opens named pipe for reading or writing, kernel awakes other processes that were asleep. Whether a particular process is going to be read particular data, other process stop. Whenever first process completes it reading, then other processes wake up for writing, and vice versa. If a process opens a named pipe for reading and a writing process exits, when a process opens a named pipe for reading and writing process exits, the system call completes. That is, all reading and writing process, that is this system call completes. If the process opens named pipe with no delay option, the open returns immediately, even there are no writing processes. But if neither condition is true, but if neither condition is true, the process leaves until a writer process opens a pipe. Similar rule hold for a process that opens pipe for reading. So a pipe should be viewed as a processes write into one end of pipe and read from the other end. A pipe should be viewed as a process write into the one end of a pipe and read from other end. As mentioned, a process access data from a pipe in a first out manner, meaning that the order that data is written into pipe is the order that read the data from that pipe. That is the order from which we have read the data. In the same order we can write into the pipe. So number of process reading from the pipe do not necessarily equal number of process writing to the pipe. That is, if the number of process reading up from the pipe, there is no need to equal number of processes writing in the pipe. If the number of readers or number of writers greater than one, they must coordinate use of pipe with other mechanisms. The kernel access data for a pipe exactly as access data for a regular file. Kernel access the data for pipe, which is exactly equal to access data for a regular file. It stores data on pipe device and assigns block to the pipe as needed during write calls. The difference between storage allocation for pipe and regular file is that a pipe uses only direct block of the inode for greater efficiency. The storage allocation in case of pipe usually direct blocks of inode for greater efficiency, although this places limit on how much data a pipe can hold at a time. There is a certain limit on that pipe, how much data can be hold at a time. The kernel manipulates direct blocks of the inode in a circular queue. The kernel manipulates direct blocks of inode into circular queue, maintaining read and write pointers internally to perceive the file, that is first in first out order. So execution of pipe in circular queue also there is first in first out manner. We can read and write the pipes. So consider there are four cases for reading and writing the pipes. First, writing a pipe has a room for a data being written. Writing a pipe that has a room for the data being written. Reading from a pipe that contains enough data to satisfy the read. Reading from a file from a pipe that contains enough data to satisfy read. Third condition, reading from a pipe that does not contain enough data to satisfy the read. And finally, writing a pipe does not have room for data being written. So in these four cases, first two cases satisfies their conditions. That is, first condition shows that the writing pipe, assume that pipe has a room for the data being written. That is, sum of number of bytes being written and number of bytes already in the pipe in the less than or equal to pipe's capacity. So number of blocks or number of rooms exist in a pipe are more than the data should be written. Similarly, in second case, for reading a pipe contains enough data to satisfy the read. That is, reading the capacity of reading the contents of the pipe that is greater than the data is stored in that pipe. So these two conditions satisfies their reading and writing purpose. But third condition for reading pipe does not have a data fulfillment to satisfy the read condition or enough data to satisfy the read condition. Similarly, in case of files, there is no particular space or less space as data being written. So kernel follows the algorithm for writing a regular file, except that it increments the pipe size automatically after every write. So for writing a regular file, kernel follows the algorithm for increment the file size automatically after every write, since by definition amount of data in the pipe grows with every write, and this differs from the growth of regular file where the process increments the file size, where the process increments the file size only when it writes data beyond the current end of that file. If the next byte offset, if the next byte offset in a pipe where to require use of indirect block, the kernel adjusts the file offset value in the user area to point to the beginning of the pipe, that is byte will start with offset 0. The kernel never overwrites data in the pipe. Kernel never overwrites data in the pipes. It can reset byte offset to 0 because it has directly determined that data will not overflow the pipe's capacity. When the writer process has written, when the writer process has written all its data into the pipe, the kernel updates the pipe's write pointer so that next process to write the pipe will proceed from where the last write is stopped. So next writing kernel updates a write pointer where the last write stopped. From that point, the next process will start for writing the contents of the pipe. The kernel then awakens all other processes that fell asleep, waiting to read the data from the pipe. When a process reads a pipe, it checks the pipe is empty or not. Whenever the process start is process going to read, then first check the pipe is empty or not. If the pipe contains data, then kernel reads the data from that pipe. And if the pipe were regular file, then follow the regular algorithm for read. However, its initial offset is the pipe read pointer stored. That is, first file pointer were stored indicates the extent of the previous read. That is, previous read stopped point indicates that from that point the process is going to be read towards next. So after reading each block, kernel decrements the size of pipe. After reading of each block, kernel decrements the size of pipe according to the number of bytes it read. In case of read, kernel increments the size of pipe according to the number of bytes it write. Here, in case of read, after reading each block, kernel decrements the size of pipe according to number of bytes it read, and it adjusts the user area offset value to wrap around the beginning of pipe if it is necessary. When the when the read system call completes, the kernel awakens all sleeping writer process and set the current read offset to the inode. If a process attempts to read more data than is in the pipe, if a process attempts to read more data than is in the pipe, the read will complete successfully after returning all data currently in the pipe. Even though it does not satisfy the user count. If the pipe is empty, the process will typically sleep until other process writes data into that pipe. If the pipe is empty, then the process will goes to the sleep mode while other processes that is writes data into that pipe, at which time all sleeping processes were waiting for data, wake up and race to read that pipe. If, however, a process open a named pipe with the no delay option, if a process opens a named pipe with the no delay option, it will return immediately from a read if the pipe contains no data. The semantics of reading and writing pipes are similar to the semantics of reading and writing terminal devices, allowing programs to ignore the type of file they are dealing with. So, reading and writing of pipes are similar to the reading and writing terminal devices. If the process writes a pipe, the pipe cannot hold all the data. If a process writes a pipe, the pipe cannot hold all data. The kernel marks the inode and goes to the sleep waiting for data to drain from the pipe. When other process subsequently reads from the pipe, when other process subsequently reads from the pipe, kernel will notice that processes are asleep, waiting for data to drain from the pipe, and it will awaken them as explained. The exception to this statement, when a process writes the amount of data greater than the pipe, the capacity, when the process writes the amount of data greater than the pipe capacity, here kernel writes as much data as possible to the pipe, puts to the process to the sleep until more room becomes available. Thus, it is possible that return data will not be contiguous in the pipe if other processes write their data to the pipe before these process resume its write. So analyzing the implementation of pipes, process interface is consistent with that of regular files, but the implementation differs because kernel stores the read and write offsets in the inode instead of file table. The kernel must store offsets in the inode for named pipes so that processes can share their values. They cannot share values stored in the file table entries because processes gets a new file table entry for each open call. However, sharing of read or write offsets in the inode predi- predates the implementation of named pipes. Processes with access to named pipes share access to the pipe through common file table entries, so they could conceivably store, read, or write offsets in the file table entry as is done for regular files. And this was not done because low level routines in the kernel no longer have access the file table entry. The code is simpler because processes share offsets stored in the inode. Then closing pipes. Up till this, now we have studied reading and writing pipes. Now we are going to study closing pipes. When closing a pipe, a process follows the same procedure it would follow for closing a regular file, except that kernel does a special processing before releasing pipes inode. Kernel decrements the number of pipe readers or writers according to the type of file descriptor. If the count of writer process drops to the zero and there are processes asleep waiting to read the data from the pipe, the kernel awakens them and return from their rest system call without reading any data. If the count of reader process drops to zero, there are processes asleep waiting to write data to the pipe. Kernel awakens them and send them to a signal to indicate an error condition. In both cases, it makes no sense to allow the processes to continue sleeping when there is no hope that the state of pipe will ever change. If a process is waiting to read an unnamed pipe, there are no more writer processes. There will never be a writer process. Although it is possible to get new reader or writer processes for named pipes, the kernel treats them consistently with unnamed pipes. If no reader or writer processes access the pipe, if no reader or writer processes access the pipe, the kernel frees all its data blocks and adjusts the inode to indicate that pipe is empty. When it releases the inode of an ordinary pipe, it frees the disk copy for a reassignment. See, this is the algorithm or programming code for reading and writing a pipe. So here character string hello. Then in main function we have declared buffer array, buffer character array with size 10 24. Then there are two pointers, character pointers, cp1 and cp2. Integer file descriptors array with size 2. So cp1 is equal to string, cp2 is equal to buffer, while then increment in pointer 2, which is equal to increment in pointer 1. then pipe file descriptors, and this for loop executes infinitely, writes the file descriptor 1 buffer and with the reference number 6, read the file descriptor. Initially reading concept is 0 buffer and with reference number 6. Why here reference number 6 has taken? See, the length of string is a string length of string hello is 5 and end of this string with null character, that is a sixth character. So here reference number 6 is taken. The process creates a pipe and goes to an infinite loop, writing the string hello into the pipe and reading them into the pipe. The kernel does not know or nor does it care that the process that writes the pipe in the same process that it reads the pipe. Kernel does not care whatever data has been read by the process. The same data is written by the process or not. This is program code for reading and writing for named pipe. Same as previously. Here character array, string character array, that is hello. Then main function with different arguments, argument c and argument v. Then in file descriptor character buffer with size 256, that is create named pipe with read or write permission for all users. Then make a node first in first out manner. Then file descriptor number, then reference 0. If argument c is equal to 0, then file descriptor is equal to open with first in first out manner for a read for a write only purpose. If this condition becomes false, argument is equal to 2, this condition becomes false, so go to the open file in first out manner for a read only. Execute the for loop infinite time. Then check if argument c is equal to 2, then write file descriptor, then string with reference 6, otherwise read file descriptor buffer with reference 6. So a process executing the program creates named pipe node called as first in first out. If invoked with a second or dummy argument, it continuously writes the string hello into the pipe. It invoked if the invoked without second argument, the read the named pipe. The two processes are invocation of the identical programs, have secretly agreed to communicate through the named pipe first in first out, but the need not be related. Other users could execute the program and participate in, that is interfere with the conversation. Then next system call is duplication, short form dup. This system call copies the file descriptor into the first free slot of the user file descriptor table, returning a new file descriptor to the user. It works for all the file types. The syntax of this system call is new file descriptor new fd is equal to duplication of file descriptor, where fd is a file descriptor being duplicated and new fd is the new file descriptor that references the file. Because of dup duplicates the file descriptor, it increments the count of the corresponding file table entry, which now has one more file descriptor entry that points to it. See this figure carefully. See in this figure here, in the user file descriptor table, this is user file descriptor table, this is file descriptor table, and this is inode table. So in user file descriptor table, at third location, here file is opened for suppose a reading purpose. The file which is etc password. In this example, the opened file is etc password at third location. Suppose it is opened first time for reading purpose. Similarly, at fifth location, the same file is opened for writing purpose. So here count is 1. Initially, whenever at third location it is opened, initially count is 1, but at a sixth location the same file is opened for reading purpose. So here count is 2, and for reading purpose and for writing purpose, so here count is 2 in the inode, one for reading purpose and other for writing purpose. So the etc password file is opened at descriptor, that is fd3 at third location, then opened file local at fourth location, and opened file etc password at fifth location, and finally duplicated the file descriptor at 3 at sixth location. So duplication is perhaps as elegant system call because it assumes that the user knows that the system with return lowest numbered free entry. Duplicate, perhaps it is elegant system call because it assumes that the user knows that the system will return the lowest numbered free entry in the user file descriptor table. However, it serves an important purpose in building sophisticated programs, from simpler building blocks programs as simplified in the construction of shale pipelines. See, this is a simple program of duplication system call. In this program, here declared integer ij, character array, two arrays buffer 1 and buffer 2 with size 512. Then I is equal to open file name and purpose of that file. So file name here, etc. password, and here read only by other group. J is equal to duplication of I. So read that value of I, buffer size 1 and buffer 1 and size of buffer 1. Similarly, read J, buffer 2 and size of buffer 2, close I, then read J, buffer 2 and size of buffer 2. Here, the variable I contains the file descriptor that the system returns as a result of opening file, etc. password. Here, I indicates or value of I indicates that file descriptor system returns the result of opening a file, and J contains the system returns a result of duplicating file descriptor or I. In the user area, the process, the two user file descriptor entries are represented by the variable user variable I and J point to the new file table entry and therefore use of the same file offset. The first two reads in the process. This is a red color line and blue color line. These two entries, the read data in sequence, and the two buffers, buffer 1 and buffer 2, and do not contain the same data. This differs from the case where the process open the same file twice and read the same data twice. A process can close either file descriptor if it wants, but input output continues normally on the other file descriptor. In a particular, a process can close its standard input output file descriptor, the duplication of other file descriptors, so that it becomes the file descriptor 1. Then it treats that file as a standard output. Then next, a system calls as mounting and unmounting. Unmounting, also known as U mounting file systems. A physical disk unit consists of several logical sections partitioned by disk driver. Each section has a device file name. Processes can access data in a section by opening an appropriate device file name and then reading and writing file, treating it as a sequence of disk blocks. The amount of system calls connects the file system in specified section of the disk to the existing file system hierarchy. The mount system call connects the file system into specified section of the disk to the existing file system hierarchy, and the umount system call disconnects the file system from the hierarchy. The mount system call connects the file system to specified section to the disk in the file system hierarchy, whereas the umount system call disconnects the file system from the hierarchy. The mount system call thus allows user to access data into the disk section in the file system instead of sequence of the disk blocks. The syntax of mount system call is mount and three parameters such as special path name, directory path name, and option that is read only, write only, or execute only. So here special path name is the name of device, special path, special file of the disk section containing file system to be mounted. Directory path name is the directory in the existing hierarchy where the file system will be mounted, called as mount point, and option indicates where the file system should be mounted, that is read only. See this figure carefully. See in this figure, if a process issues a system call mount device and then disk 1 user 0. So in this file, this is a root. Then for this file system, there is binary file, etc. file, user file. Now user file becomes as a root, and user file, that is, there is again binary file, include file, and source file. So kernel attaches this device disk file to the user at a zeroth location with zero reference. So kernel attaches this file containing partition disk called as a device disk 1 to the directory user in the existing file system tree. The file device disk 1 is a block special file, meaning that it is a name of a block device, typically a part portion of the disk. Kernel assumes that indicated portion of the disk contains the file system with a super block, inode list, and a root inode. After completion of the mount system call, the root of the mounted file system is accessed by the name user. Processes can access the files to the mounted file system and ignore the fact that it is detachable. Only the link system call check, only the link system call check the file system of a file, because the system file does not allow the file links to span multiple file systems. So each mount table entry contains a device number that identifies the mounted file system, a pointer to a buffer containing file system superblock, a pointer to the root inode of the mounted file system, a pointer to the inode of the directory to that mount point, association of mount point inode, the root inode to the mounted, association of mount point to the root inode mounted file system set up during the mount system call allows kernel to traverse file system hierarchy gracefully without special user knowledge. Then this is the algorithm for mounting a file system. Algorithm mount input for this algorithm, that is file name of block, special file directory name of mount point will be option, that is read only. Output is none. If it is not super user, then return error. Get inode for block special file with the help of algorithm name I. Make legality checks. Get inode for mounted on. Directory name with algorithm name. If not a directory or a reference count is greater than 1, then release inodes with the help of IPut algorithm and a return error. Find empty slot in mount table. Invoke block device driver open routine. Get free buffer from buffer cache. Read super block into free buffer. Initialize super block fields. Get a root inode of mounted device with the help of iGet algorithm. Save in mount table. Mark inode of mounted on directory as mount point with the help of algorithm I put for releasing a special file inode. Unlock inode of mount point directory. See this algorithm carefully. So kernel only allows processes owned by a super user to mount or to unmount, that is umount file system, yielding permission for mount and umount. The entire user commonly would allow malicious users to wreak havoc on file system. Super users should wreak havoc only by accident. So mounting and unmounting file system. Kernel finds inode of special file that represents the file system to be mounted. Extract the major and minor numbers that identify the appropriate disk section, and finds the inode of the directory on which file system will be mounted. The reference count of the directory inode must be greater than 1 because potentially dangerous side effects. It must be at least 1. The reference count number of directory inode must not be greater than 1. It must be at least 1 because potentially dangerous side effects. Because greater than 1, there are some reference numbers. And that's why a reference count of the directory must not greater than 1, at least up to 1. So kernel then allocates free slots in the mount table, marks to the slot in use, and assigns the device number field in the mount table. The above assignments are done immediately because the calling process could go to the sleep. In the ensuing device open procedures or reading the system superblock, and another process could attempt to mount a file system. By having marked the mount table entry in the use, the kernel prevents the two mounts from using the same entry. By noting the device number of the attempts mount, the kernel can prevent other processes from the mounting the same file system again, because strange things could happen if the double mount were allowed. So there is only single mount permission is allowed. The kernel call open procedures for block device containing the file system in the same way it invokes the procedure when opening the block device directly. The device open procedure typically checks that the device is legal, sometimes initializing a driver data structures and sending initialization commands to the hardware. Kernel then allocates a free buffer Kernel then allocates a free buffer from the buffer pool to hold super block of the mounted file system and reads the super block using variation of the algorithm read. The kernel stores the pointer to the inode of mounted on the directory of the original file tree to allow file path names containing dot dot to traverse the mount point. It finds the root inode of the mounted file system. It stores a pointer to the inode in the mount table. To the user mounted on directory, the root of the mounted file is logically equivalent to the kernel establishes their equivalence by their coexistence in the mount table entry. Processes can no longer access the inode of the mounted on directory. The kernel initializes field in the file system superblock, clearing the lock fields for the free block list and free inode list, and setting the number of free inodes in the superblock to 0. The purpose of the initializations is to minimize the danger of the file system corruption when mounting the file system after the system crash, making the kernel think that there are no free inodes in the superblock forces algorithm I alloc to search the disk for free inodes. See this figure. See, this is the figure for inode table and mount table. So this mount table, that is super block mounted on inode root inode. So here mounted on inode marked as mount point as a reference count is 1. Here is no reference, not device is in use, so reference count is 0. Here again reference count is 1 and buffer of the system. So unfortunately, if the linked list of the free disk block is corrupt, the kernel does not fix the list internally. If the user mounts the file system read only to disallow all write operations to the file system, the kernel sets the flag to the super block. Finally, kernel marks the mounted on the inode as mount point, so other processes can later identify it. Figure shows the various data structures at the conclusion of the mount call. So crossing mount points in the file path names. Let us consider algorithm name I and I gate for the cases where path name crosses the mount point. The two cases for crossing the mount point are crossing from the mounted on the file system to the mounted file system. Crossing from the mounted on file system to the mounted file system, that is in the direction from the global system root towards a leaf node, and crossing from the mounted file system to the mounted on the file. This following sequence illustrates the two cases here: mount, device, then disk 1, then user. So here user is a root directory of disk 1, device disk 1, and mount on that. So cd change, that is change directory from user to source to uts, that is dot 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 dot. So the mount command invokes, that is first line, the mount command invokes the mount system call. After doing some consistency check, mounts the file system in disk section identified by dev disk 1 onto the directory user. The first cd, that is change directory command, that is middle one line, causes a shell to the execute change directory system call, and kernel parses the path name crossing the mount point at user. The second cd command results kernel parsing the path name crossing the mount point at third dot dot in the path name. So this algorithm for accessing inode, see this algorithm carefully.
This is the algorithm for accessing an inode. Algorithm IGATE. Input file system inode number. Output load inode. While here algorithm IGATE input file system inode number. Output locked inode. While it is not done, if it is true, then go to the if statement inode in inode cache. If it is true, then check inode is locked or not. If it is locked, then go to the sleep and continue sleeping mode until event inode becomes unlocked. Special processing for mount points. If the inode a mount point, if it is true, then find mount table entry for mount point. Get new file system number from the mount table. Use root inode number in search and continue this loop again. If inode on inode is free list, remove from the free list and increment the inode reference count and return inode. If inode not in inode cache, then remove new inode from the free list. Reset inode number and file system. Remove inode from old hash queue and place on new one. Read inode from the disk algorithm with the help of algorithm B read, that is buffer read. Initialize inode, that is reference count is equal to 1, and then return inode. This is the algorithm for accessing inode. So for crossing mount points in a file path names, for the case of crossing the mount point from the mounted on the file system to the mounted file system, consider the revised revised algorithm for IGATE in previous program. If the inode is marked mounted on, the kernel knows that it is a mount point. It finds the mount table entry which mounted on inode is the one just accessed and notes the device number of the mounted file system. Using the device number and inode number for root, use the common to all the file systems. It then access the root inode of the mounted device and returns that inode. In the first chance change directory example of in previous slides, the kernel first access the inode for the user.
in the mounted on the file system, finds the inode marked on the mounted on, finds the root inode to the mounted, finds the root inode of the mounted file system in mount table and accesses the root inode of the mounted file system. Then this is algorithm for parsing a file name. Algorithm name I, which converts path name to inode. Input path name, output locked inode. If path name starts from root working inode, that is root inode, with the help of iGet algorithm, else working inode, that is current directory inode, with the help of iGet algorithm. If there are more than one path names, then read the next path name component from the input. Verify the inode of the directory permissions. If the inode of the is a component, that is dot dot, then continue component search. Read inode directory with the help of algorithm bmap, bread, and brelease. If the component matches a directory entry, get the inode number for matched component. If found inode of the root and working inode is root and component name is dot dot, then get mount table entry for working inode. Release working inode with the algorithm I put. Working inode mounted on the inode, log the mounted on the inode. Increment a reference count of the working inode. Go to the component search for dot dot. Release the working inode with the help of input algorithm. Working inode is equal to inode for new inode number, that is iGet algorithm. Else component not in directory, that is return no inode, return working inode. So for the second case of crossing mount point of the mounted table system to the mounted on the file system, consider this revised algorithm for name I in this program. After finding the inode number, a path name component is a directory. The kernel checks of the inode number is the root inode of the file system. If it is already present, otherwise if the inode of the current working directory is also root and path name component is dot dot, the kernel identifies the inode as mount point. So crossing mount points in a file path names, it finds the mount table entry whose device number equal to the device number of last found inode. I gets the inode of the mounted on the directory, continues its search for dot dot using mounted on inode for working inode. At the root of the file, however, dot dot is a root. The example, uh, previous example, that is cd dot dot slash dot dot slash dot dot, assume that the starting current directory of the processes is user slash source slash uts. When parsing a path name in the name I, the starting working inode is current directory. The kernel changes the working inode of that of slash user slash source as a result of parsing first, that is dot dot, in the path name. Then it parses the second dot dot, the path name, and finds the root inode in the previously mounted user and marks and makes the working inode in name I. Finally, it passes a third dot dot in the path name. It finds that the inode number for dot dot is the root of the inode number. Its working inode of the root inode, that is dot dot, the current path name component. The kernel finds the mount table entry for user mount point, releases current working inode, the root of the user file system, that is, and allocates the mounted on inode, that is the inode for the directory user in the root file system as new working inode. Then it searches the directory structures in the mounted on, that is user, for that is user searches the directory structures mounted on user for dot dot and finds inode of the root of that file system, that is root. Then the change directory system call then completes unusual as usual. The calling process is obvious to the fact that crossed to the mount point. Then this is the algorithm for unmounting a file system. Algorithm: you mount, input a special file name of the file system to be unmounted, output none. If the it is not super user, then return error. Get inodes of special file with the help of algorithm name I. Extract major minor number of the device being unmounted. Get mount table entry based on major minor number for unmounting file system. Release inode of special file with the help of algorithm I put. Remove shared text entries from the region table for table belongs to the file system. Update super block inodes if flush buffers. If files from the file system still in use, then return error. Get root inode of the mounted file system from the mount table. Lock inode. Release inode with the help of IPUT algorithm. Invoked close routine for special device. Invalidate buffers in pull from unmounted file system. Get inode of the mount point from the mount table. Lock inode. Clear flag marking as mount point. Release inode with the help of IPUT algorithm. Free buffer used for super block. Free mount table slot. This is the algorithm for unmounting for file system. So syntax for unmounting system call is unmount with parameter special file name, where special file name indicates that file system to be unmounted. When unmounting file system, kernel accesses the inode of the device to be unmounted, retrieves the device number for special file, releases inode with the help of IPUT algorithm,
finds the mount table entry whose device number is equal to that of special file. Before the kernel actually unmounts a file system, before the kernel actually unmounts the file system, it makes sure that no files on that file system are still in use by searching the inode table for all files whose device number equal to that of the system being unmounted. Active files have a positive reference count and include files that are the current directory of some process, files with shared text that are currently being executed, and open files that have not been closed. If any files from the file system are active, the umount, that is unmounts, call fails. If it were to be succeed, the active files would be inaccessible. The buffer pool may still the buffer pool may still contain delayed write blocks that were not be written on the disk, so the kernel flushes them from the buffer pool. The kernel removes assured text entries that are in the region table but not operational, writes out all recently modified super blocks to the disk, and updates the disk copy of all inodes that need updating. It would suffix for the kernel to update disk blocks, super blocks, and inodes for unmounting file system only, but for historical reasons, it does so for all the file systems. The kernel then releases the root inode of the mounted the file system held since its original access during the mount system call and invoke driver of the device that contains the file system to close the device. Afterwards, it goes the through the buffer in the buffer cache and invalidates the buffers for the blocks on the new unmounted system. There is no need to cache data in those blocks any longer. When invalidating the buffer, it moves the buffer to the beginning of the buffer free list so that valid blocks remain in the buffer cache longer. User area clears the mounted on the flag in the mounted on inside set during the mount call and releases the inode. After marking the mount table entry free for the general use, the unmount call completes. Next system call is link. The link system call links a file. The next system call is link. The link system call links a file to a new name in the file directory structure, creating new directory entry in existing inode. Syntax of this link system call is link Then source file name, target file name, where source file name is existing file name and target file name is a new file name or additional file name that will have after completion of the link call. The file system contains path name for each link file has, and a processes can access the file by a path names. The kernel does not know which name was original file, and no file name is treated specially. For example, after executing system calls, that is first statement indicates that user source UTS system. This is a source file, and this is user includes and system. This is a target files. Then user includes a relief source file, and this is a test file.h. This is a target file. So there are three path names for these files, that is user source UTS system test file.h, or user include system test file.h, or user include real file. So we will study link and unlink system calls in next lecture. Now we are going to stop here. If you have any query, then please ask. Otherwise, write your roll number in chat box and leave the session.